Hi, I'm Caitlin Chafee from Rhode Island Coastal Resources Management Council, and I just had a quick question for Tom. I was wondering if you have looked at all at possible interactions between the elevated CO2 levels and nitrogen and pore water salinity, if there's any interaction that you've looked at.
We have data on it, but I haven't really explored that data set completely. So I mean, we're a brackish system there, so our salinity there is anything between 8 to 14, depending upon the year and rainfall. I think that's part of the interannual variability, but I haven't looked specifically at that in depth. But we have the data to do it.
Hi, this is a message for Tom. Also, a question for Tom. Liz Durkee, Oak Bluffs Conservation Commission. Did I hear you say that managing Phragmites to decrease nitrogen would have a negative impact on sea level rise and carbon sink values?
Potentially. So, I mean, what the data is suggesting is, you know, nitrogen will increase Phragmites growth and invasion rates, and that's going to increase growth both above and below ground. It's one thing we've been talking about. It's the, you know, we talk about C3 plants can respond to CO2, grasses respond to nitrogen, but no plants can respond to both global change factors. And what we're suggesting is that Phragmites may be that one plant that can respond. So if we add nitrogen, you know, it'll be good for Phragmites, and it's good for surface elevation gain to a point, because if it gets too high in elevation, you know, it's going to respire away. But nitrogen may be good if you want to convert to a Phragmites wetland, perhaps. I'm not advocating it by any means, but the data sort of hints at that. I'm not saying that we should be converting these marshes to Phragmites, but I think more of the thing is, if we don't want Phragmites, well, then we should limit nitrogen loading. But nitrogen will increase plant growth, which will increase below ground. You know, we see this enormous response below ground, which will help the marsh keep pace with sea level rise to a certain point. But I wouldn't say do it. Yeah.
Any other hands?
Hi, Tom. I'm also for the town of Oak Bluffs, and on the with the Phragmites, we've been discussing if there's some way we can manage around it and and use it to remove nitrogen, such as harvesting it before it flowers and finding another a use for the Phragmites, perhaps just as compost. We've been told that some farm animals do eat it, but we don't know the nutritional value on it. And then cutting it again in the fall. Has any of that type of thing been talked about?
So we know that, I just published a paper saying that goats can be used to, you know, goats will, you know, control Phragmites if you pen them up. It's not their preferred food choice, but I mean, other countries actually produce Phragmites. If you can believe it, I was in Kmart and I found reed fences that were Phragmites imported from China. So believe it or not, we're actually importing Phragmites here, which blows my mind that it's worth it for us to import it and sell like these little tiki torch fences. But I mean, people use it for paper production in Hungary. Like, there are other uses, but I mean, that's a great entrepreneurial decision. Can we make some other use? I mean, we don't have, thatch roofs aren't very popular here. It's the best thatching material out there, but yeah.
So Kathy, this one's for you, and I mentioned it when you came back, but I think one thing to think about on that conceptual model is maybe, and for the audience to consider, is that there may be a third axis there. So as you had below ground productivity and then the soil type, but where you are on that, kind of in that, the term that's been thrown around a lot this morning is the elevation capital. So where you are in the tidal frame may, on the organic rich side, may change the shape of that curve. So I'm just wondering if you had any thoughts on that or thoughts for the audience.
Yes, I would agree with Kristen that you do need to take into account the elevation of the marsh and where the marsh is located relative to mean high water, which would link to the flooding regime that the marsh receives, because that will affect the sulfate reduction and the anaerobic conditions that provide for sulfate reduction to be carried out, and that would cause the increase in sulfite. So I think it's a good idea, and I think I'll add that third axis. So thank you.
Thank you. John Cashmore with the Nature Conservancy. I just had a question for Kathleen. Based on the Plum Island side-by-side you had for how the fertilizer was applied, whether it was in the water or on the vegetation, I'm just wondering what we know about why we have such drastic differences.
Well, I think that it still remains a research area, but some of the ideas that have been proposed are, for one, the difference in elevation. So those two locations are at different elevations. In Lyndon Deegan's experiment, the source of the nutrient addition was in the creek water. So the face of the creek was exposed immediately and to the greatest extent with regard to the rest of the marsh, even though it would still percolate through the soil to other areas of the marsh. In Jim Morris's experiment, which was up in the high marsh on the platform, it was at a higher elevation. So it didn't see the same flooding that the creek bank saw. In addition, another hypothesis is that the vector for the nutrient addition was different between the two experiments. So in Lyndon Deegan's experiment, the nutrients were added to the water, so they were applied during the flooding tide, where in Jim Morris's experiment, they were solid pellets. So there could be a difference in the actual vector for applying it. Jim Morris's experiment, they put the pellets into the soil, so it would directly get into the pore water, and they do have high levels of nutrients in the pore water that the plants can use to grow, and they have higher above and below ground production. So I think elevation is really important. So where you are in terms of mean high water and being flooded, because that interaction of the nutrients and the seawater are going to affect the biogeochemistry in the soil.
That was just a fabulous series of talks. I'm curious whether any of you think that, given the range that you represented here from like 1 to 300, I guess it was kilograms of nitrogen per meter squared. I think I took it to that. I did the math. I can't remember now, but yeah, 300 grams. Never mind. 1 to 300.
Right.
Can we start to? I know there's difference in the timing of it and all these other differences. Can we start to at least set maybe a threshold number that, like, do not cross this number, do not cross, and then we'll have a problem? Because the only place I really saw a problem was Jamaica Bay, where we were at 300 grams. Actually, that was milligrams per meter squared per day, but it was like 300 times what they were seeing in Wacoit. I'm just curious if you do think that there's maybe not the answer on yes, no, nitrogen, but just a absolute no, like a far end, do not cross this line.
Well, I'll take the first stab at that, but I'm sure we have other people who want to comment. I think it's not only the concentration of the nutrients that are being delivered to the system, but also the length of time for which it is applied. So I think you'd have to consider both aspects of the nutrient enrichment. And the other aspect, I think, that is important that I mentioned earlier in my talk was the soil matrix, I think, is important. As far as the threshold, at this point, we don't have really enough information to say the threshold because of that, the confounding effects. When we think about restoring marshes sometimes now, we think about, if we're adding sand, I mean, it matters what you add when you're restoring a marsh. In some ways, by adding a more sandy amendment could buy you decades of time for the marsh to grow because it's more sandy. So I think Charlie Roman and Don Cahoon are writing a paper right now about those efforts at Jamaica Bay, where they did a lot of thin layer sediment application and the amount of time they bought because of the type of material they had applied to build elevation with this sandy mix.
Sure. I was going to say one thing, sort of going on what Kathy said a moment ago. I think that our current understanding needs some reevaluation with respect to thresholds and nitrogen delivery. Because, I've been working the TIDE project as well, and, how we calculate your nitrogen loading rates are based on, how much most of our loading rates are based on hydrodynamic models, how much the residence time of the water exchange, and that gives us the nitrogen loading rate. But the real question is how much of it really stays there. So even my plot level studies, we go out there with a backpack sprayer and we spray on the water and it sort of stays there resident. So that gives us a direct response. We can see it, but when we're applying nutrients at this larger gradient, what we're noticing is that these plot level studies don't necessarily scale up. And I think I'm not really comfortable putting a number of a threshold. I think there is a threshold that, it's gonna go bad. But I think we need to really think about, as we're thinking forward and designing new experiments, how are we really applying the nitrogen and what's the real loading rate? Because as Kathy said, when Jim puts in 60 grams of nitrogen per meter squared per year, he's putting in ammonium chloride, which is gonna stay put. But we know a lot of the nitrogen coming to our systems is nitrate. As an anion, it's very mobile and it doesn't stay. It's got a very low residence time, so it's gonna come in and go out. And I think we need more research really to figure out how long is that nitrogen really staying there. But that's sort of, I have a paper right now that we're writing up to sort of compare the plot level stuff to like these big ecosystem studies. And I think it's a direction that needs more research, clearly. Because the Iroquois Bay stuff is mainly nitrate coming in.
Well, also, I was going to follow up on that because I've thought a lot about the form of nitrogen, but in Iroquois Bay, a lot of our nitrogen is coming in by groundwater discharge, and and the form is that it's then being used by phytoplankton and it's becoming particulate. And so the salt marshes might actually be seeing particulate nitrogen, and that might be the addition that they're seeing. And that's a completely different game changer than ammonium or nitrate. Right. So then we might have 3 different forms. Mm-hmm. Yeah.
So I would just agree and summarize some of the comments that our reply is that thresholds depend on the form of nitrogen, the amount of nitrogen, and the spatial scale or temporal scale across which they've been applied to try and help us synthesize the results we presented just today, which is a subset of the work that's being done in this field. I generated the plot behind me, which is showing the annual nitrogen loads for the variety of experiments that we've discussed. And so the small circle in the bottom corner is Iroquois Bay. I think it's relatively safe to say that these nitrogen loads didn't cross some critical threshold in terms of ecosystem level respiration. In contrast to Narragansett Bay, where maybe we do have some issues there. We're on one of the very highest edges in terms of nitrogen loads. But what's interesting, I think, and that points to the multiple factors needing to be considered, is if you look at the Winyah Bay, South Carolina case, which is below 50 grams of nitrogen per meter squared per year, that's kind of similar to what's been applied at Plum Island that's led to this Nature paper about marsh collapse due to nitrogen loading, and yet at very similar levels Winyah Bay was doing just great and benefiting from the fertilization. So that's one case where the nitrogen level alone cannot dictate the response, and as Kathy explained, that was probably due to the high sedimentation rates, mineral inputs there that we lack here. So unfortunately, there are multiple factors, and then just within looking at nitrogen, there are many reasons why we need to not compare apples to oranges in defining the threshold.
So I know Kevin touched on this in his introduction. Oh, thank you. It was like looking at a headlight. So we're talking about the thresholds for salt marshes, and these salt marshes are all tied to the estuaries. And I think it's pretty clear from Iroquois Bay, at least, that the negative impacts of the moderate level of nitrogen loading that we're seeing are pretty significant in terms of the Iroquois Bay estuary ecosystem function. And so we might not think necessarily, what's the threshold for a salt marsh, but what's the threshold for the entire ecosystem that the salt marsh is in? And it's clearly lower than what the salt marsh itself can handle. So that might be something thinking in terms, I know that's something that the Steve's talk a lot about, is really thinking about not just one part of your ecosystem, but your kind of ecosystem landscape. And so that clearly comes out, I think, in our research, that that's what you need to consider.
I just like to repeat again, yes, for the Iroquois Bay, in terms of gas flux and biomass, in that range of nitrogen, we have not found any kind of negative impact from those nitrogen loading in the salt marsh itself. But yes, nitrogen, where the nitrogen go? Basically, still there's some nitrogen loading there. I think some of them actually basically stay in the soil, basically used by microbes. The others may be used by phytoplankton or wash away to the estuary. I think the estuary may be influenced the other kind of food web in that system. But in terms of salt marsh itself, I think that amount of loading is below the threshold we can see.
I'd just add to that, we're talking about blue carbon, and seagrass is a big part of that. And so historically, seagrass was present, was it not, in Iroquois Bay? And it was present, was it not, in Narragansett Bay? And so let's be cautious about shifting baselines. And if we want to actually say, you know, what was the critical threshold for nitrogen loading, maybe we did exceed it, and we missed the response.
Thank you all very much. My name is Carrie, and I'm from the University of Maryland. I'm a postdoc working at the Chesapeake Bay Nears Reserves. And a question for Tom. You spoke briefly about the possible phenological changes of the Phragmites. And I just was wondering if you could elaborate, especially since I saw you had a fixed growing season length, and I know specifically in Chesapeake Bay, we're seeing an extension of the growing season length. Whether it's earlier and going later, and if that will have an impact on the changes you're observing.
Right, so one thing we've noticed is that when we have nitrogen, the plants grow earlier and they grow later. So everything it received, the model was simulating, because we measured photosynthetic rates every month from May to November. So what that model was capturing is looking at the carbon gain throughout those different months. And what we found is that when you add nitrogen, the plants stay greener longer. And because they're greener longer, they're able to gain more carbon. That was just sort of an observation after the first year. I'm like, wait a second, how come like some of the chambers were already senesced? And then I noticed that like half of them were still green much longer. So that's what we sort of put 2 and 2 together, is that when you add the nitrogen, it sort of allows them to just hold on to their leaves longer and allows them to photosynthesize longer. It's probably because they don't need to remineralize that nitrogen because there's maybe a surplus of it. So.
Yeah, question for Tom. The thing that Rose Martin's work, I was looking around quickly for her poster on the frag work that was done up in Iroquois Bay. And, of course, she's Serena's student. So maybe Serena could say the thing that we've noticed, we caught that sort of the carbon uptake and the interesting stuff there, but we're seeing that, high methane release. So, I mean, it's early times in that experiment, but in terms of figuring out what the carbon sequestration and the total greenhouse gas flux, we're beginning to think that as we spoke about yesterday, it's that methane release that is looking like the big gorilla from these marshes, and so maybe that just has to be taken into consideration with the frag as well to put it in the right perspective.
Yeah, I mean, it's a great question. So we actually have some data on methane emissions as well, except we didn't have the analyzer in place when we did it. So we only have methane release, and we don't have, Serena and Rose have these really great data with GPP and methane release, and we only have methane emissions. So we are seeing as well, similarly, when you shift communities, we're also seeing enhanced methane emissions, and the real question is now, can we close that balance? And in my current experimental design, the chambers haven't been completely taken over by Phragmites, so it's really hard to make that prediction. We're going to try to maybe wait a little bit longer. Once it has invaded more, then we can sort of set up some of those sort of little chambers inside to really make some questions. But as you said, it's a really good question. I mean, in brackish systems and salt marsh systems, I don't think methane will be, it's going to be increased, but the real question is, I forget the puffin, anything above 18 parts per thousand, we just have so much sulfate, there isn't as much methane. But once we get into those brackish marshes, it's a really big question there and needs a lot of more research. It would be fascinating.
One quick comment is about methane flux. I think it can be released both from the soil sediment and from the plants itself. Mm-hmm. I think the ratio from those different pathway is still not very clear. I think that's why we need to understand more about the pathway of methane, either from plants and from soil. If plants, and how density and how species influence those emissions of methane from the system.
And I'd like just to mention that yesterday we had talked a bit about other benefits that different marsh systems provide, and I think that's another consideration here when we think about letting a system become a homogeneous stand of one species like Phragmites. to think about what might happen to other services, including what habitat it might provide, how it might act as flood abatement, its resistance to storm surges. I think some of those areas are not well investigated, but I do think we don't want to lose sight of other benefits that we want to consider when we look at blue carbon in these different systems.
Like I said, I don't advocate, planting Phragmites. Just one thing. What my real question is, management. Where are the management dollars best put? There's places where we can have a successful restoration. If you have small, isolated estuaries, pristine reserves, something where we can have effective management. I wholeheartedly agree with Phragmites restoration and abatement. But the problem is when you get these huge 100-acre marshes. We're never going to restore it, or it's going to be really, really challenging to restore it. So places like that, we have to pick and choose our battles. Those might be places that we just want to let go because we're beyond that point of management. And, the question is, it can be good, but I don't think, we have limited dollars for restoration, so we need to pick and choose where we want to restore. So sometimes it's just better just to leave it alone.
I just wanted to add quickly in terms of the question of the kind of blue carbon value of Phragmites. Rose and Serena's paper pretty clearly showed a huge CO2 uptake. There was an increased methane flux as well, but the global warming potential or impacts of that methane was less than the CO2 uptake. But it's, I think based on their study, and maybe Tom, you may be able to add something to the question, the fate of the carbon that's taken up from the atmosphere is different in Phragmites than in Spartina. There's a lot more in biomass, and that biomass hangs around for a long time. The stems are going to wash away as particulate matter, and the long-term fate of that, it may not be known. It may not be that it's a long-term uptake, as would be the case with storage in the soil. Do you have any information on how much of the carbon is going into the soil versus what goes into the stems?
So I have lots I don't know off the top of my head. I know a lot of the carbon does go below ground into the soils. I've done just mesocosm experiments as well, and there is at least the 2-to-1 ratio between, above ground and below ground. So what we're seeing above ground is it's a really small fraction. I mean, I showed you that below ground biomass data, we had roots down to 3 meters, and I think that was like a 6, so if I'm correct, I think it was like a 6-to-1 above to below ground ratio. So what we're measuring above ground is really a small fraction of what's below ground.
Okay.
So I think that there's a lot more, just because of its ability to root so much deeper, and there's just so much more mass, I think that it really can be a bigger sink. Now the question then becomes, methane and are there offsets in it? But,
okay.
But I think there is that definite potential. I don't know with Serena as well, if you've seen other data. Yeah, it's hard to go that deep, and it's out like months of, Justin spent about 3 months going through those cores.
Thanks again to the presenters, and I hope you enjoy your lunch.